Hello everyone, the problem that we'll look at today is the USACO 2023 US Open Contest Silver Problem 1 of Milk Sum. You can pause the video first and read through the problem yourself. You can see the statement is quite lengthy, but the actual process should be straightforward. So basically, you have n cows with n being 1.5 times 10 to the fifth power. I don't know why it's 1.5, but you have that many cows, and now you're trying to milk all of them in a certain order. Each cow is to be milked have a milk production number, which is AI. So for the ith cow, it produces AI units of milk per minute. And now you're trying to unhook these cows. So at first, all of these cows are hooked to a milking machine. And for every minute the ith cow is hooked, it produces AI units of milk. And now you unhook them one by one. So the first cow unhooked is unhooked after just 1 minute of milking. So it only contributes 1 minute of milk. And the second cow is unhooked after 2 minutes, and so on. And now you're trying to determine the optimal order to unhook these cows to yield the maximum total milk production. But you're then given Q queries. For each of them, you basically change the order of this cow being unhooked. So let's take a look. It's curious how T will be affected if some of the milk production values in his herds were different. So each query is specified by ij, meaning that a new value of T of AI is set to J, then what will be the new total amount of milk produced? So essentially, a cow now produces more milk or less milk, but notice that each time only one value is changed, and after every single query, this value is to be restored. So in summary, basically you have n cows, and then you're trying to unhook them in optimal order, but you have to answer Q queries for each of them. You change the milk production per minute of one of the cows by a certain number, but after every query, you restore it to the original amount. And now you're trying to determine, after we unhook them in the optimal order, what is the maximum total milk production. And you can see the first cow is unhooked after 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. And then the optimal order is obviously the least producing cow, we hook it for the least time, and then the most producing cow, we hook it for the longest time. Okay, so now you can pause video once again and think about how to solve this yourself. Should be quite simple, at least for US Open Silver. Okay, so for these problems, I don't really even know what trick this will be called, but I guess prefix sum. So notice how you can really just determine the order of the cows very easily, as we already seen in the sample. It's just the least producing cows are hooked for the least time, and the most productive cows are hooked for the longest time, because, well, the total amount of time is set, and we're trying to give these minutes to the cows that can give us the most milk per minute. So it makes sense to do that. So now each time we change it, we can quickly find what this order this cow will be unhooked is after the change, and we already know what it is before the change. So then if we bring up a drawing board, say we have these cows, and cow I originally is unhooked here, so that's original. And then after we increase this milk production, obviously we want to unhook it later because the milk production is increased. It's now inserted in this new spot, and we're unhooking the cow I, right? So the milk production is added by a certain amount, say num, right? And now notice that the milk produced by all of these cows and the milk produced by all of those cows do not change. It's just the milk produced by these middle cows, the cows that are within the original production number and the new production number. Those are the cows which the amount of milk produced is changed, and it's just shifted parallelly by a unit of 1 to the left, right? And if the milk production is decreased, we will want to move the cow to unhook it earlier. In that case, these will be shifted to the right by 1. And all of the shifting left, shifting right can all be done very simply by just a prefix sum. And then finding the new spot from the original spot and the amount added can also be done in the log n complexity just using a binary search, because, well, as we know, we don't actually have to insert it. It's the milking. Okay, The milk production is resetted after each time. What is happening to my computer? The milk production is to reset after each query, which means we don't have to actually insert it. We just use the same array each time, and we binary search the optimal spot to insert the cow. And here is my code, which, as you can see, pretty fast. So first of all, we have to keep track of the original spot of the first original value of the cow, pardon me, and then we sort them using the original value. And then we calculate the prefix sum. And then for each of the new, obviously if the milk production didn't change, we just output the original answer. Otherwise, we do a binary search that finds the new spot. And then after the binary search, okay, y when y is smaller, we do a binary search that's different from the bigger. So that's something you have to note. The binary search process is a little bit different. I guess you can use lower bound or upper bound, but I do not prefer STL binary search algorithms because those sometimes give you runtime error. After we've done the binary search, we know where the new spot is and we know where the old spot is. We can use the prefix summary that we calculated to find the change in the production of this region. However, we also have to find the change in production of this singular cow, which can obviously easily be calculated just using the number of spots is shifted to the right or to the left. We'll just output the answer, and notice how it's answer n, and it does not affect the original answer up here that we calculated, because the original answer is because the milk production is to be restored after every query. So the new answer does not renew the original answer. And that is it. Pretty simple and straightforward, right? So when we come back to the problem today, it is not that complicated. And I would say we don't really even need any trick for it. It's just you look at it and you're like, hey, I think we just stored them and that'll give us the maximum production, and you verify it. It's like, yeah, that makes sense. And then for each time, you notice you can easily find where the new spot is, and then you just kind of draw a graph yourself and notice how the left side and the right side doesn't change. So then you can just very intuitively just find the prefix sum and then find the value after the shifting to the left or to the right of the middle zone, and then you just find the change in value of this singular one, which is even easier to achieve. So hopefully after this video, you'll know how to solve the USACO 2023 US Open Contest Silver Problem 1 of milk sum. And thank you for watching. I hope this video helped. See you tomorrow. Alright, that was a problem review, and now if you're just looking for the solution to this problem, you can go ahead and click out of this video. For today, I'm not like really slacking off anymore because I still did something, but the problem I did is let's see, it's a pretty, I don't know, the problem is it's not any template or anything, it's just pretty weird one where you use a double pointer that looks like a double pointer, but it's not really a double pointer, but then you also have a very great observation, so I would call it observation problem maybe. Here we have is literally called a string. So you're given a string A consisting of characters from lowercase English characters, and then you try to delete each character one by one. Not one by one. We define SI by the string after deleting AI from the original string, and now you're trying to sort S1 through Sn lexicographically. So to achieve that, essentially we use a double pointer kind of technique, but it's not double pointer. Because we notice that for these sorting problems, usually what we do is to find these relative relationships that always stay true. In this case, we just kind of play around for a bit, and then we find, say we have this situation here. We have a bunch of j's that are the same, and then we have an I that is greater than a j. Notice how no matter what we delete that's after this, if we delete j, Sj is always going to be lexicographically larger than whatever we delete if the deletion happens after I, right? Because think about it, it'll just be like this. We delete j, and then we have this. So since I is greater than j, this spot of I is basically shifted to the left by 1, and which now this corresponding spot has a j on it. So this one that occurred after deleting a j must be lexicographically greater than this one that occurred after deleting any later numbers, including I itself. So yeah. Yeah, that's how you solve it. And so I would say that's a pretty decent difficulty observation problem. I would say if I was back in January or maybe even February, I probably would have solved it. But well, now we're in April and I can't. I had to look at the editorial solution and well, yeah, at least I understood, right? And then I've been doing a lot of templates recently. Gaussian elimination, that's Cartesian tree, that's hash. No, that's hash, and there's K and P. Okay, so that's a ground report. Pretty good. See you tomorrow.